Thank you. My name is Keegan. I'm one of the core developers who helped create Matrix, and I'd like to spend some time talking to you about federation. The aim is to try to give you a deeper understanding about how Matrix's federation actually works. It isn't necessarily going to help you write a home server, although there will be some tools that you may be able to use that will actually help you. So first of all, what is the Federation API? So hopefully this is all kind of familiar, that most people have used the client-server API. The Federation API is the way that two home servers will talk to each other. That's a bit high level, so you could go a bit deeper than that. So here's the server-server API with all the HTTP endpoints, all the JSON objects, and that basically tells you everything you need to know. So that's it. Thank you very much. But in all seriousness, what is the Federation API really, and what makes it hard to understand, right? Because it is a set of HTTP APIs and is a way to exchange JSON. It is also a pub/sub mechanism if you have devices updates, for example. But the main thing that makes it hard is that last one, the way to synchronize data structures. In this case, it's the rooms. How do you synchronize rooms between servers? And that's what I'd like to talk to you about. A few of the constraints that Matrix has is we want these kind of properties, right? So we want it to be open, so anyone who has a server should be able to participate. There shouldn't be any single points of failure, so no central server that if you can't talk to it or if it goes down, then you can't communicate, particularly communicate to other users who are on your own server. So the fact that you can't talk to some other server shouldn't matter. Likewise works during net splits, so there's network partitions. It shouldn't matter. Your users on your server should still always be able to communicate. And it needs to be Byzantine fault tolerant because the internet is a scary place and people get up to all sorts of mischief. So you need to have a protocol that's going to tolerate that. So if we had more time, I would explain how I build up to CRDTs, but we don't have time, so you're just going to have to go with me for now. But if you don't know what a CRDT is, this is the Wikipedia definition, along with some bold and underlined bits which detail the relevance to Matrix here. So the first one is mentioning effectively that it's working during net splits. The second one indicates there's some sort of merge algorithm. For us, this is the state resolution algorithm. And then the last bullet point there is basically saying that if you've seen the same events, then you are in the same state, so your room state, for example. And the term conflict-free is a little bit misleading because in general, CRDTs can't prevent conflicts, but they do give you a deterministic way to resolve those conflicts. If all of that went over your head, you can think it's kind of like Git, but with automatic merge resolution. So as a kind of way of thinking about this. The thing with CRDTs is they're quite special because they prioritize AP of CAP theorem. So they're prioritizing availability and partition tolerance at the cost of consistency. The consistency guarantees they can give you are quite strong. In fact, they call it strong eventual consistency in the literature, which basically consists of the 2 points I've mentioned there, eventual update and convergence. So eventual update being that if one correct server sees some event, then everyone else is going to see the same event. They may not apply that event, but they will see it. And then convergence, that once you've applied all the same events, you will be in the same end state. The key thing that makes this different from most other forms of distributed systems is that there's no consensus mechanism. So if you're familiar with blockchains and stuff, you have the idea of 51% attack. If you have more than 51% of the hash rate, then you can kind of control the direction of where the chain goes. You can't do that with this. Likewise with things like Raft and IBFT, those are CP-style systems. So the moment that you can't talk to, you don't have a majority in a network partition, then your system doesn't work. So we're going to be talking about delta state CRDTs. Now, if you know CRDTs, that's fine. If you don't, there's a few different types of CRDTs. I'm talking about delta state CRDTs because that's effectively what Matrix is. And I'm also, if you look at CRDTs, most of them will talk about it in a peer-to-peer-like manner. I'm not going to do it. I'm going to talk to it in a federation-like manner, which again mirrors what Matrix actually does. So you've got A and B who are going to be exchanging some stuff. We're going to be implementing a set as opposed to exchanging messages, but you'll see it all comes very similar. In the middle here, you're going to see the operations that are going to be performed. Some of those operations will be done concurrently. That's why the graph splits. And each one of these servers is going to walk along explore this graph in a slightly different way. So first of all, red adds pizza to the set. which then you can see this little red line has appeared at the top there to see that the server has seen up to the pizza event, and then that event gets propagated over to the blue server, who then also applies it. Then you can have the blue guy adds beer to the set, which then gets applied, and then concurrently red does the same thing, because who doesn't like beer? And of course now you've got two beers in existence, but it's a set, so we actually only care about it once. And then the operations get exchanged between the two servers, and then we have applied the same updates, and therefore we are in the same state, which is that there is pizza and beer in the set. Now what happens is a merge operation, because now the next event that happens is someone decides they don't like beer anymore, and they remove beer from the set. Now, what happens here is application defined. Because we are implementing a set, we probably want to remove beer from the set entirely. If this was a counter, right, in which case we've added the beer thing twice, then we might just want to decrement by 1. But because we're implementing a set, we're going to remove beer from the set entirely and then propagate that over. And as you can see how the two servers have explored this graph, they eventually have seen the same events and they are in the same state. So it's worth noting that this could have gone slightly differently. So for example, if we concurrently add those beers again, before A and B could communicate that they've both added beer, perhaps there was a network partition or something that they couldn't exchange updates. And now the blue guy is going to come along and delete the beer as before. So in this case, the graph shape is different, right? Because the delete is not pointing to both of the adds, it's only pointing to one of them because it hasn't seen the other one. But the state on this guy is the same as it was before, but on this guy it's going to be different, because what the blue server is now going to say is they're going to say, I'm going to add beer, and I'm going to immediately remove the beer that I just made, which effectively is a no-op. And then at some point, the red server is going to go and send the beer that they did add, and then you'll end up, again, converging on the same state. Now, what happens here is application defined as well. So concurrently, you've got beer added and beer removed, but because this is a set, we want to, the fact that there were two beers added and only one removed, there's still beer in the set. However, if the delete here was a ban and the add beer was, say, the person who is being banned, they're changing the room name, then you're going to want that delete to overwrite what happened with the add. So it's application defined, exactly the semantics that's done here. And we're going to keep coming back to this, as you'll see in a moment. Everything I've described up until now is not Byzantine fault tolerant, because you can choose what those IDs are, and it's very sensitive to which IDs you choose. So one of the key things that you can do is you can have a hash linked DAG, which is what Matrix does, where the ID is the hash of the event JSON itself, and then in that event JSON you include the previous events. So that's forming a DAG structure, and they're all hash linked together. This is mostly to make it so you can't create an event that collides with an already existing event, because if you can do that, you can break causality. Senders can be spoofed, so naturally you should sign your events. That's hopefully obvious. Lots of systems do this. And the third one is interesting as well, because the third one is that updates can be dropped. If there are malicious servers and you are only going to talk to certain malicious servers, they can just drop all your updates, in which case you're not going to converge, you're not going to see the same updates, and that's not good. So Matrix has a point-to-point architecture at the moment, which means that we get around this problem. It obviously is not very performant. We'd like to fix that, maybe with something like random gossiping, but at the moment we don't. But that is partly for security reasons. But if you combine these things, you end up with a Byzantine fault-tolerant system that can cope with an arbitrary number of bad actors. So it's immune to civil attacks, which I was alluding to earlier with the 51% attack. Hopefully, this is all looking very familiar at this point, because the hash link DAG, the signatures, the routing, all the little graphs with the DAG forming, that's literally what Matrix is at the federation level. And we wrote a tool, or actually Matthew wrote a tool back in 2020 called TARDIS, which is a way of effectively visualizing this graph in matrix rooms. And it looks a bit like that. And all it does is it takes a JSON file, and then it will render the events that are in that JSON file. And the key thing, which I added in a couple months ago, was to then be able to perform state resolution on those events. So I think hopefully I can go and give a quick demo of this. Right, so this is TARDIS. No, this is nothing. Well, that's awkward.
Welcome to my world.
Screen mirroring, currently extending, change to entire screen? This one?
Yeah. Literally what I did to go.
Right. Okay, cool. It's a bit weird, but okay, fine, sure. And now if I do this, so you can see here's a graph of a room. These are rooms that are fake. They're not from a real room. There's not a real Alice and Bob here. But TARDIS allows you to inject fake events, and it will calculate events and do all sorts of stuff for you. But you can see here there are concurrent operations being done here. That's why the graph is forked. And you can see that concurrently what's happened is Alice has removed Bob's permissions, and on another branch, so concurrently, Bob did not know this, Bob made Charlie a mod, and then Charlie went and set the room name. So what we want semantically is we prefer safety over liveness. We don't want bad things to happen. So we're going to stop Bob making Charlie an admin, and we're going to stop Charlie from setting the room name. So if you hit resolve state here, which actually may not work because I'm not sure if I'm running the... yeah, that's fine. I am running it. There we go. So if I hit resolve state here, you can see that some of these nodes have gone green. So this is the result of state resolution. So what this means is that at this event, which is this end event, this is what the room state is. So you can see at the room state, once these two forks have been merged, Charlie is not a moderator, and the room name has not been set by Charlie either. But what you can do is you can go back in time and see, back here before these operations were done, then the actions had been applied, right? Because it's optimistically applying these updates. This is why sometimes if you have concurrent behavior and then you can talk, your servers can talk to each other once again, you might see state get rolled back, because if something has happened like this, there's been a concurrent revocation which you weren't aware of, then we have to decide what's going to happen under those circumstances. And what we decide is that you're not going to be able to. We prefer whatever the admins want to do, effectively sorted by power. But I will get onto that. Right, now if I go back to here, like that, there we go. Okay, cool. So, state resolution. State resolution, so hopefully I've convinced you that state resolution algorithm and CRDTs merge algorithms are basically the same thing, and we just need to decide on what the rules are for concurrent behavior. And that's effectively what the state resolution algorithm does. Like I said before, it's application defined, and we prefer safety over liveness. So I'm going to go through the state resolution algorithm at like a medium-ish level. I'm lying in a few places, but in essence, I'm mostly not lying. It's only small technicalities in my defense, but it makes it easier to explain. So here you've got two forks you want to merge, and they have some sort of shared state where they originate from, which is the stuff in yellowy orange. The stuff in yellowy orange is perhaps, obviously called unconflicted state because it's not conflicted between the two forks. The blue and red stuff is conflicted, but the blue and red stuff may contain events that, like if one of those was setting the room name, well, that may not be conflicted, but the making the person a moderator is conflicted. So you need to include all the authorization events in this conflicted set. So that's basically where we pull in, okay, you're changing the room name, okay, but you also now need to include the power level event that made you a moderator. It's that sort of thing. Once you've done that, there's two stages to the state resolution algorithm. The first one only deals with a subset of the room state called power events. So in power events, these are power levels and things that can revoke the ability for people to do certain actions. We're going to take the events and we're going to order them. We're going to split them based on the full conflicted set, and we're going to order them based in what the specification says, the reverse topological power ordering, which is a set of ordering rules which initially is honoring the causal relationships. Then when there is no causal relationship because it's concurrent, we're preferring power levels and then tie breaking on timestamps and event IDs. Once we've done that, we're going to go and apply iterative auth checks. So we're going to use the unconflicted set as the base state, and then we're going to go through each event in turn and see if the event passes iterative auth checks. If they don't pass, then we won't include them in the final set. So once we've done this, we take the stuff that we did get, and that will be called the partially resolved state. It's partially resolved because we're only dealing with a subset of the events here. And then the second step is to handle all the other remaining events that we didn't handle before. Things like setting the room name, setting the room topic, that sort of thing. And again, similarly, we need to order these events. So we're going to compare each event to where it sits on the power level mainline. Every single state event points to a power level event, which gives it the authorization for that action to have taken place. And if you use that, you can then basically use that as a primary ordering mechanism. Now, some of those events may have been rejected from the earlier iterative auth checks that were applied, like in this scenario that we're about to see. If that happens, then you just go to the earlier power level event. But if you keep doing this, then you will end up with an ordered set of remaining state events. Wait for the animation. There we go. That's called the mainline ordering because it's based on the power level mainline. And then again, we're going to do a very similar thing. We're going to use the partially resolved state this time, and again apply iterative auth checks. And likewise, iterative auth checks may reject certain events or not. And then the result of that becomes the final resolved state. And that's mostly how this algorithm works. A few things that most of the stuff I've touched upon. So yeah, unconflicted set is things that both folks agree on. The power events are things that may remove the ability for you to do certain actions. The power level mainline, the reason why this exists is because we want to split room state we want to split room state into epochs effectively. Like if there's concurrent behavior, you need to try to order the events in a way that isn't just using the timestamp, which can be gamed. So we use the power level mainline to order things roughly causally. So the state resolution algorithm is not infallible. Okay, it isn't perfect. There are cases where it behaves in ways we do not expect it to behave. And part of this is, well, most of this is down to the fact that servers are walking this graph in different ways and therefore processing events in different orders. And this is due to connectivity issues predominantly. And if we know of certain failure modes, that's great. We can look at them in TARDIS and we can resolve them, make sure everything works or doesn't work. But it'd be nice if we could kind of discover new failure modes and discover new ways that things can break. So this is introducing a new tool, which has only recently been released, called Chaos. Chaos uses similar stuff which I've done before with Complement and Complement Crypto. It runs home servers and Docker containers, and it uses a man-in-the-middle proxy to sniff on the Federation traffic. And it can also modify the Federation traffic to just reject the traffic entirely to cause partition faults. Likewise, we also introduce crash faults by sig-killing home servers at random or at determined times. So the best way to do this will be to demo this one as well. Okay, so I did manage. Oh, yeah, that's fine. So can I do that? Okay. So, thanks. So here is Chaos. Chaos has got two clients on different home servers. These are real home servers, by the way. And you can hit start, and what's going to happen is it's going to send lots of client-server API traffic and then lots of Federation traffic that you're going to see at the bottom there, and you can see everything's happy. You can then hit net split, which will then block the traffic. So every time they try to send a request, it will say blocked. And then you can, at some point, heal the net split. And then what's going to happen is it's going to reconcile the state, and you'll see a bunch of extra requests being made. There you go, which is it kind of resynchronizing what the room state is effectively. And then you can hit test. And now what test is going to do is it's going to ensure that the room membership list on the client on home server 1 and home server 2 matches, is in agreement, and also matches what chaos believes is the room state, because they should all three of those should match, and chaos is like the gold state of what it should be. And you can see here it said success because the room state did match. So using this as a tool, we can introduce net splits, we can crash the home servers, and we can do, the idea behind this is to kind of have one of these guys running until something bad happens, and then we can see what went wrong. So I will just close that down and then go to here. And the other thing is, obviously, you can run this without the web UI, in which case you just get more of a log-like sort of thing. So you can see the federation requests going through there. Each tick is the number of client-server API requests, and then you'll see at some point it'll say net split, and it'll block some traffic. There you go. So that's been a really useful tool for us to investigate improvements to the Federation API protocol. So yeah, the kind of thing is why make these tools at all in the first place? And mostly it's to develop, to make some changes to the Federation API to make it more secure and to make it more performant as well. So we've been working quite closely with academia, particularly Florian Jakob, and we're going to be we'll be proposing some protocol changes to the Federation API just to make it a bit more robust to various faults. If you want to read any more, feel free to take a picture of this. This is some academic papers which talk about CRDTs in more detail, and particularly in relation to matrix as well. So would highly recommend going through those if you're interested. And thank you very much.
We have some time for questions.
How do you differentiate failure modes from malicious attacks? Please repeat the question.
Yeah, how do you differentiate failure modes from malicious attacks? Ultimately, you can't, right? Because a malicious attack could be just partitioning off the network. Something like chaos only does non-malicious attacks, so we're talking crash and partition faults. It's very hard to automatically model malicious attacks because it may be altering certain fields in the event or altering signatures or like something like that. So we can't automate automate testing for them. If we see stuff in the wild, then obviously we can go and see kind of what went wrong, but there is limits to what you can do there, at least automatically.
Can you use this for deterministic fuzzing and non-deterministic fuzzing?
Can you use this?
Fuzz?
Am I going to make it fuzz? Well, effectively it kind of does already, because it will run until there is a failure either on the client-server API or on the Federation API. So in that way, it is already a fuzz tool. I would like to make it deterministic. So there was a talk yesterday in the testing room, which I went to, about deterministic simulation testing. And if you've ever seen the Tiger Beetle presentation, that's the sort of stuff I'm talking about. And that was inspiration for chaos. I would love to have that, but to do that, you need to effectively re-engineer your home server so you can mock out things like your network I/O, your disk I/O, and clocks. So that's quite an undertaking, and isn't something which we don't really have time to do right now. So, but maybe in the future.
Yes. So you were talking about applications being application specific to decide how to resolve a conflict. Can we then see maybe in certain matrix implementations or something like that you can then maybe as a sort of super moderator choose how to resolve certain conflicts, especially with moderator rights and everything? I could imagine that could be something like malicious moderators taking over with their own home servers and then having some attack vector there, but then as an application developer being able to then leave the moderation in some way, shape or form to... Ultimately,
no. So the question, so the question is basically, can you at a per room level define what the application-specific merge algorithm is going to be, and let it up to be more of a social problem, and say this moderator is going to say these are the rules? Ultimately, no, because all servers need to come to an agreement. So just because one guy says this is what you should do to merge things, the other servers all have to agree, and why should they agree what your server says? So it has to be baked into the protocol.
Yeah, thank you.
Over there?
Yeah, just it kind of goes in the same direction. I was wondering when Matthew talks a lot about matrix in other contexts, like, I don't know, IoT or whatever use case, might that in the future require changes to the state resolution algorithm where these kind of application-specific conflict solutions are not usable outside of the message context?
Yeah, so this is Matthew wanting to use Matrix for non-messaging IoT or things like that, and does it require changes to the application-defined merge algorithms? Yes, I think so. I think at some point we may want to have the ability to put additional CRDTs on top of Matrix. I mean, that's just what I think, but I agree. At some point, you're going to want more complex structures, which then need to have additional rules for how you handle mergers.
Two questions left.
Nico has a question.
Oh, you have a question. Hello.
Are you looking mostly only at the state resolution, or are you also looking at how other layers of Matrix, possibly the server key infrastructure and stuff, then affect the state resolution?
Yes. I mean, sorry. So are we looking only at state resolution, or are we looking at other parts of the Federation API as well? We are looking at other parts of the Federation API. We are looking at server keys. We're also looking at the way that we reconcile state for partial synchronization. So if you've been offline for a very long time and you need to catch up, then what we currently do versus what we could do, kind of thing. We are looking into that, yeah.
And Chaos looks into the internal state of some home server, right?
No.
So
Chaos does not look into the
it's
internal state of the home
usable
server.
with another implementation.
Yes. Yeah. So it's all it needs is the client server API and the Federation API. And in fact, the main thing it does to intercept it all is you literally just set HTTP proxy, the environment variable. You set that to a man-in-the-middle proxy. That's basically all you need to do. So it's really easy to get it working with your conduits and your dendrites of the world. So
Thank you, Keegan. I was
Thank you.
really impressed by the visuals you used in the demonstration and also in the tools and by the naming of the tools. Thank you very much, and thank you for explaining.
thank you.